Ladies and gentlemen, Professor Eugen Wren.
Yeah, thank you for inviting me to this prestigious place with such a beautiful view and such wonderful activities, and it's an honor for me to be part of it. Thank you also for the very nice and generous introduction. And I would like to start my talk with a few impressions of our current developments in the Anthropocene. You have followed this summer the burning of the rainforest. Is that loud enough? And of course, this is not a natural event, but it's an effect of the extension of land use in different forms, the usage of wood, but in particular, the rapid expansion of agriculture. And it's not just a local event. I could show you similar pictures of burning woods from all over the world. But even just in Latin America, the Amazonas, if this reaches 20%, then the entire ecosystem is at risk to collapse. So this is just the most recent development. And before I go more deeply into the Anthropocene, I want to deal with the history of science. I'm a historian of science, so I want to ask the question, what does the Anthropocene, what can it possibly mean for the history of science, or as we now say, for the history of knowledge? Which new perspectives does it entail? Is it just the next fashionable turn? Evidently, there are many perspectives on the history of science, and we tend to think of some of them now as being outdated. In my view, however, even in view of the challenges of the Anthropocene, also the older, more traditional approaches to the history of science, such as the careful exegesis of texts or detailed reconstructions of cognitive processes, have by no means become obsolete. I think we should get out of the habit of following fashions or turns and playing different methodological approaches or knowledge interests off against each other. They may all be valuable in their own right and will probably continue to be so in the future. What is more important, I believe, they complement each other. Only by taking such a pluralistic approach can we guard against ideological prejudices and muster the intellectual resources necessary to confront the serious intellectual and practical challenges with which the Anthropocene confronts us. Such complementarity and open-mindedness is indeed needed when considering the complex material, social, and mental dynamics that mark humanity's transformation into a geological force shaping our planet. Take, for example, the so-called material turn of the history of science. This has clearly demonstrated the productive role of epistemic objects, experimental systems, and large-scale infrastructures. Its one-sided radicalization, however, may also lead to an underestimation of the mental, social, and political dimensions of knowledge systems that we need in order to understand the coupling of the development of science and technology with extractive economy, with the extractive economy responsible for the ongoing environmental changes. Or take the social constructivist attempt to understand scientific practice, for instance, from the perspective of epistemic virtues. While this has given new insights into cultural context and their role for the production and validation of scientific knowledge, it focuses almost exclusively on local settings, often at the expense of the larger economic and political contexts relevant to the understanding of the Anthropocene. The currently widespread trend of moving from history of science to history of knowledge has brought long-neglected dimensions also of scientific knowledge into focus, such as intuitive, practical, and craft knowledge within and outside of the sciences. Today, we see historical scientific knowledge more and more as the tip of an iceberg whose substance is manifold forms of world knowledge, such as the practical knowledge of Renaissance engineers and artisans crucial to the scientific revolution. The history of knowledge has opened up new vistas for the history of science, also by paying greater attention to environmental and global history, for instance, by taking into account the global circulation of knowledge on plants and animals. A highly diluted history of knowledge may run, however, also the danger of losing track of science itself. It may thus fail to consider the central role that science and technology have played and are still playing for the onset of the Anthropocene, and no longer take as a challenge the special role they appear to have for other cultural processes. A history of knowledge, on the other hand, rightly denies the older history of progress and other grand narratives, but it offers instead little in their place. At least no grand narrative, for all I can see. Can the Anthropocene concept perhaps help us to develop a novel, overarching intellectual framework binding together the different approaches to the history of science? Before I come back to this question, let me take a step back and ask, why are we doing the history of science? Do we still follow the motives of the Enlightenment? Do we still hope for science as a model for reason, as the Vienna Circle once did? Or is the history of science rather a counter-movement that criticizes the dominance of certain forms of rationality, or even the epistemic division of subject and object in the name of a new Gaia philosophy, allegedly in response to the challenges of the Anthropocene? Are we concerned with justice, for instance, global or gender justice, or are we pursuing the history of science purely for the sake of knowledge? Can a history of knowledge critically accompany science and perhaps even draw attention to neglected alternatives, suppressed or missing knowledge? Within the history of science, such motives often remain implicit, but we should keep reminding ourselves that approaches to the history of science based on topical issues are legitimate and should not be dismissed lightly with the thoughtless blanket judgment of Whiggishness. The Anthropocene is precisely one of these current challenges. The term Anthropocene was first suggested in 2000 by the atmospheric chemist and Nobel Prize winner Paul Crutzen at a conference in Mexico City on Earth system research. Crutzen suddenly felt an aversion to the characterization of the present state as part of the Holocene, as this seemed to downplay the influence of humankind on the Earth system. He urged the delegates to stop using the term Holocene and sought a better term, even during his lecture. We are no longer in the Holocene, we are in the Anthropocene, he spontaneously uttered. It later transpired that the term had an even longer history or prehistory. In my view, the history of science and the history of knowledge can make a decisive contribution to the understanding of the Anthropocene, but only if they overcome the one-sidedness of current approaches that still tend to focus on highly localized narratives or on fashionable viewpoints. In other words, the theme of the Anthropocene is also an opportunity for the history of science to break out of its occasionally scholastic or postmodern fragmentation in order to confront a much larger picture. At the same time, it invites us to bring together many lessons of the past. Without extending the history of science to a history of knowledge, the Anthropocene can hardly be tackled with, nor can it be understood without taking into account long-term development processes and global history. In the face of the Anthropocene, there can be no question of a history of progress, of course, but rather of an evolutionary history of knowledge for which material, cognitive, and social dimensions are equally relevant. By means of science and technology, the human race has massively changed the planet, and with dramatic consequences. Some of these changes have taken place at a much faster pace than natural processes. There is barely any pristine nature on the planet. A large part of the Earth's surface that is not covered by ice has been transformed. The polar ice is melting, the ocean's water level is rising, and coastal and marine habitats are being massively transformed. More than half of Earth's freshwater is exploited by humans. Oceans are being acidified and contaminated by aquacultures and plastic. The construction of dams and extensive deforestation is massively affecting water circulation and erosion rates, and therefore the evolution and geographical spread of numerous species are endangered. The loss of biodiversity is much greater by orders of magnitude than it would have been without human intervention. On average, every second nitrogen atom in the biosphere has been processed once by the fertilizer industry. Most of the biomass of all living mammals is made up by humans and domesticated animals. Through energy-intensive chemical processes, humans have created functional materials, which are rare under natural circumstances, and brought them into wide circulation. Among these are elemental aluminium, lead, cadmium, and mercury, fly ash residues from high-temperature combustion of coal and oil, and also concrete, plastic, and other man-made materials, many of them displaying properties that are alien to the natural world. Plutonium from atmospheric nuclear testing will persist in the sedimentary record for the next several 100,000 years as it decays into uranium and then into lead. We are measuring the highest atmospheric concentration of the greenhouse gases, carbon dioxide and methane, in at least 800,000 years. Even if the use of fossil energy resources were to stop immediately, which I think it should, it would take thousands of years before that concentration will sink again to pre-industrial levels. Sorry, I didn't show you this really striking curve that shows the CO2 concentration and the level that we have reached above what we have reached in the last 800,000 years. But what is also remarkable, you can also see that from that curve, some of these changes have occurred at a much brisker pace than natural processes. The present concentration of carbon dioxide has been reached at a rate that is at least 10 and possibly 100 times faster than any time during the last 420,000 years. Simultaneously, new diseases have spread through carriers whose rapid life cycles allow them to adapt quickly to new conditions. But how quickly will human societies adapt to the new conditions? Ongoing changes will affect, of course, different parts of the globe in different ways, and the global nature of these changes will not always be easy to recognize for those who suffer from them. Developed countries may actually appear to benefit from climate change, while developing countries suffer. But ultimately, everyone will lose. There is no protection, not even for the rich. In short, the Earth is changing with irrevocable consequences. There is no hope of ever returning to a natural state of things. People do not act against the backdrop of unchangeable nature, but are deeply interwoven with the Earth system and shape both its immediate and its distant future. And if you look not just at temporal rises, but at the deviations from the average global temperature, the changes seem to be even more drastic. And that also goes when you look at local fluctuations of weather patterns. They are much more dramatic than these sort of average curves that you normally see. So the fundamental revision of our understanding of the predicament of our planet can be compared with the revolutions of the physical conceptions of space and time, which were the direct consequences of Einstein's theories of relativity. In classical physics, space and time appear to be the fixed stage on which world events take place. Following Einstein's theory, however, this stage is no longer fixed, but is part of the piece itself. There is no longer an absolute distinction between the actors and the stage. Space and time do not remain in the background of physical processes, but participate in their dynamics. Just as the Earth system can no longer be conceived as a stable background and resource for our actions. The Anthropocene concept has created a bridge between geological and historical times. It is now apparent that the timescale of human history is inextricably linked with the geological timescale. Our economic metabolism consumes fossil fuels and over a period of decades consumes resources that have taken hundreds of millions of years to form. To put it in another way, we are currently burning so much coal, natural gas, and oil in the world in one single day as nature has accumulated in 500,000 days. And this tendency is rising. And just as geological time becomes historical time, our influence as a geological force makes human history into an integral part of geological history. At the same time, the Anthropocene constitutes its own completely new epoch in which geological changes take place more rapidly than in earlier geological times. In view of the massive impact of human interventions on the planet's environment, the traditional dividing lines between nature and culture have become problematic because, as Karl Marx put it, we are living in an anthropological nature that has resulted from these interventions. But when did the Anthropocene actually begin? This question has a double meaning, which has to do with its complex conceptual configuration. First of all, it is a stratigraphic question because the Anthropocene is researched as a geological epoch. The geological significance of the term is being analyzed by the Anthropocene Working Group, and here you see a picture of a workshop that we held together with the Anthropocene Working Group in Mainz. And Paul Crutzen is the elderly gentleman in the front to the right. And that working group in turn reports to the Subcommission on Quaternary Stratigraphy of the International Commission of Stratigraphy. So it's a well-structured hierarchical organization before this concept is finally approved as an official new epoch of the Earth system. Whatever the final decision of the geological experts may be, the Anthropocene concept has already opened our eyes to a fundamentally changed global environment. It is therefore fitting that there are also historians and historians of science collaborating in the Anthropocene Working Group. The sediments being investigated, for instance, the plutonium signal originating from Trinity or other early atomic bomb explosions, they result, of course, from historical, in particular scientific and technological historical processes. The current recommendation amounts to a determination of the beginning of the Anthropocene to that time immediately after the Second World War. But determining a stratigraphic starting point does not serve as a causal explanation of the dynamics carrying the planet into the Anthropocene. It's just an indicator that has to be taken on its own level as a stratigraphic evidence. This is now where other dimensions of the Anthropocene concept come into play. The Anthropocene as a concept is also the result of a new kind of earth science, a transition from geology to earth system science, whereby our planet can be understood as a nonlinear complex system with many feedback loops. According to this new understanding, the Earth system is not only subject to uniform change processes, but can also achieve tipping points that lead to such catastrophic changes as snowball Earth events, which apparently happened several times in the past of our planet. This is why some also speak of a new catastrophism. It has long been known that the biosphere has played a crucial role in such events since the beginning of its existence. Earth system scientists have realized that this may also apply to the anthroposphere, or the technosphere, as it has been called. The reconstruction of past climates on climate changes therefore plays a key role in assessing boundary conditions for the future of the global climate. The comparison of man-made global warming with previous climate events not only shows that if we continue like this, the Earth system will inevitably shift to a hothouse state in which we are exposed to completely new, extremely inhospitable living conditions at some places on the planet. It also shows that the speed of change and the state we are in has little comparison, little analog in earlier Earth history. Earth system scientists therefore speak not only of urgent political and economic measures to prevent this, but also of the need for Earth system stewardship. So this is an expression of Will Steffen, who has given here a talk, a well-known Earth system scientist from Australia, and he shows here sort of the stability landscape of future trajectories of the Earth system. And it's clear there's no return to this, pendulum swinging between different states in the interglacial, but we are driving towards a hothouse Earth, and if we want to prevent that, we have to, curate the Earth system. So this, of course, raises fundamental. So how does curating Earth system look like? First of all, if global temperature reaches 1.5 degrees more, the coral reefs may be lost worldwide. Here you see in a relatively short period from 1984 to 2016, the loss of the Arctic ice coverage, which is already dramatic. And, and if you look at human measures, like here, a nice picture, showing attempts in Switzerland to protect the Rhone Glacier, they look kind of helpless, if you agree, right? So is this Earth system stewardship? That's what we are going to do. So whatever actions we take, they will depend substantially on the knowledge available about the interaction between the Earth system and its human components. We are performing a global experiment with a system that is itself already changing. Although our interventions are knowledge-based, they always have unintended consequences. They lead to second-order changes, both of the Earth systems and of our knowledge systems and societal systems, of course. Consequently, more than ever, we have made ourselves dependent on our understanding of the human Earth system as a complex dynamic system. Understanding the evolution of knowledge is therefore also a central component of our future in the Anthropocene. So let me go back for a moment to the history of science. The first question is how did we get there? How did we enter this state? Nobody seriously wanted to destroy the planet, but some have taken bold risks, and so scientists have warned, but they often have played the role of the Cassandra, whose warning have been ignored. So, but let us come back to sort of the causal thing. So one obvious answer is the reference to industrialization, and especially to resource-consuming global capitalism. In speaking of the Anthropocene, some have therefore suggested to rather speak of the Capitalocene in order to draw attention to that part of humanity, or rather to those socioeconomic mechanisms that are mainly responsible for the accelerating dynamics of global change. But I think a semantic shift of that kind runs the risk of trivializing the problem, because what really matters is not naming the culprits, but rather understanding complex planetary process, which is not to say that there are no culprits. But we have to shape the system in the future, and so we have to understand the deep dynamics of it. But what is perhaps more in the current discussion, proposals to rename the Anthropocene destroy an important bridge that this term has created between the natural and the human sciences, And that has opened up completely new perspectives also for the history of science and technology. So if you ask me, I have no patience for this, playing around with other concepts. It's one of these, I'm sorry, humanities games, to somehow, incorporate the problem in their own intellectual frameworks. Let's confront it there together with a natural scientist. So back, the question of which processes and dynamics have led us into the Anthropocene is currently widely discussed. Proposals range from the invention of fire, the mass distinction of megafauna in the late Pleistocene through the Neolithic period, the early modern era, the Industrial Revolution, up to the so-called Great Acceleration of the 1950s. All of these milestones have left their mark on the history of the planet. The loss of biodiversity and predominance of domesticated animals and plants, the integration of geologically separated flora and fauna by the colonization of America, the rapid increase in CO2 emissions since the Industrial Revolution, the exponential increase of critical parameters of the Earth systems since the Great Acceleration, and so forth. All of these milestones have also changed human options for action, which have been expanded by science and technology, but also in terms of path dependencies that have seriously restricted our ranges of action. So sorry, I should have shown you this earlier. So this is a kind of a timeline of proposals, I think, which each have their rationale. So the large-scale entanglements between the human sphere and the Earth system can only be understood against the background of a conception of cultural evolution that confers an important role to knowledge and also to science. Conversely, this also may give a new scope to the history of science. Historical epistemology, as it has been practiced since the 1990s, has linked the history of science, philosophy, and cognitive science. The material turn has brought the history of science closer, for instance, to media studies, art history, and the technical sciences, whereas social constructivism has introduced important perspectives of sociology and science studies. But the Anthropocene can only be understood if all of these dimensions are considered, and moreover, if the fundamental challenge to understand such large-scale dynamics of cultural evolution is also taken into account. But let me turn for a moment now to cultural evolution. Cultural evolution has played very little role in the history of science, to be honest, and also very little role in the history of knowledge. But it's, of course, a field with its own dynamics and its own strong activities. But it has been largely treated in analogy to biological evolution, or more specifically, to a traditional view of biological evolution that focuses on mechanisms of heredity and selection and on the role of fitness landscapes. As a basis for an understanding of cultural evolution, this is, in my view, a reductionist view, which is rightly regarded with skepticism by most scholars from the humanities and social sciences. But from the point of view of, just to give you an idea, Richard Dawkins with his concept of meme is maybe, the most radical, perhaps also the most primitive version of it. But there have been, of course, much more sophisticated ways that have been very fruitfully applied, for instance, to the evolution of languages. So it's a very sophisticated activity. But I think still, humanists are rightly skeptic whether it can capture the complexity of human historical evolution. Because it mainly tends to emphasize statistical population dynamics, and it falls short when it comes to the understanding of the enablement, preservation, or prevention of innovation. So, but there are other traditions in biology that can fruitfully be used here. So don't look too much at the details of this diagram. I'll just give you a very generic picture here. And two other factors play an important role. I just try to indicate this. One is regulatory mechanisms governing the developmental dynamics of an organism. This is typically discussed under the label of evo-devo in biology. And the other is the role of environmental feedback loops brought by the organisms themselves. Think of Bieber constructing dams. This is discussed under the label of niche construction. So, from the perspective of cultural evolution, both are obviously crucial factors. The culture of human society is not simply a collection of memes, some of which are handed down and others not, but is subject to complex regulatory mechanisms that are traditionally the subject of the cultural and social sciences. Only a consideration of these manifold regulatory structures of social systems, think of institutions, makes a description of cultural development realistic, without reducing it to simple analogies of mechanisms of transmission or the selection of single cultural elements. And of course, human culture is essentially niche construction. That is, it consists in the construction and transmission of material environments, from architecture through infrastructure, production systems, and technology, to the symbol systems on which the transmission of knowledge and also of scientific knowledge is based. So the suggestion is to take these perspectives on board when consider a richer notion of cultural evolution. The role of knowledge is dramatically underestimated in the current, at times very technical discussion of cultural evolution. An important task for the history of science and technology could therefore be to fill this very gap, and conversely to also benefit from the broad perspective of cultural evolution, which at least tries to deal with this long time scale from, say, the Pleistocene to the big acceleration. The study of knowledge and cultural evolution could even offer important general insights into the nature of evolution. In knowledge evolution, it is obvious that constructed niches, such as the material and symbolic environments of human societies, not only revert to the evolutionary process by altering the external fitness landscape under which systems evolve, but they also function as extended components of the evolving systems themselves and thus play a regulatory role. After all, our ways of acting and thinking are essentially shaped by the historically available material and symbolic culture, which must therefore be considered as an integral part of the regulatory structures of human societies. Abstract concepts such as number, weight, space, time, or force, for example, could only be formed on the basis of certain shared experiences and their representation by material tools, artifacts, and symbol systems. The emergence of the concept of energy, for instance, was only possible once actual transformations of motive power, for instance, the replacement of human force by wind or water power and later by the steam engine, emerged historically as material practices. For the emergence of certain forms of thinking or action, such as mathematics, we may also consider the crucial role of such, we call it, external representations of knowledge as writing or symbol systems, which are part of the material culture of a society. In order to describe the role of this material culture as a platform enabling specific human practices, we thus speak of regulatory networks and niche construction, a concept that has been integrated into a vision for an extended evolution that we have been pursuing with Manfred Laubichler, a colleague from theoretical biology. Conceiving cultural evolution in this sense as an extended evolution also opens up a new perspective on the Anthropocene. From this perspective, it is important to understand how, over the course of history, regulatory structures of human societies have materialized in changes of our planetary environment, and how these changes in turn have enabled or prevented the emergence of novel regulatory structures, possibly giving rise to feedback loops, ultimately involving Earth's system dynamics and coupling human activities and Earth system cycles. A glimpse at the long-term path dependencies that are triggered by these processes is enlightening. Environmental contingencies, such as the availability of domesticable plants and animals, and historical constellations and events such as the European colonization of the Americas, may affect long-term developments even if their direct causal effect has long ceased to exist. This approach to cultural evolution may help the history of science to escape from hesitating between its traditional belief in progress and its postmodern resignation to a relativist historicism. On the one hand, an evolutionary perspective indeed entitles us to speak of functional differentiation and the accumulation of options for action. But it also forces us, on the other hand, to recognize that these may only be local adjustments and optimizations under contingent circumstances and under the narrow constraints of past dependencies, while there is no guarantee of overall progress and certainly no promise that the processes of knowledge production which have brought us into the Anthropocene will also suffice for surviving in it. In the transition from biological to cultural evolution, the role of niche construction has been transformed from one among several aspects of biological evolutions, some species do it, others don't, into an essential feature of cultural evolution, as the role of material culture and tool use for the very emergence of modern humans illustrates. Given the increasing significance of scientific and technological knowledge for mastering the challenges of the Anthropocene, we might be facing a next stage in a cascade of evolutionary processes in which, science and technology have again turned from marginal conditions of cultural evolutions into essential prerequisites for our continued existence. And, one could call it epistemic evolution, again, with no guarantee of survival. In the transition from cultural to epistemic evolution, the role of scientific knowledge may have similarly turned from an initially marginal aspect into a characteristic feature of this novel evolutionary dynamics. What it means is that our future will depend on the production of the right kind of knowledge. And of course, on the right way of distributing that knowledge and using that knowledge. So what does such a perspective entail for a history of science in the Anthropocene and the novel perspective it might address? It could, for instance, investigate the dynamics of human-environment interactions that have intensified over long periods of time and analyze the interaction of material and epistemic practices in the context of specific, what I call, knowledge economies. Knowledge economy here refers to the totality of social institutions and processes that produce, reproduce, circulate, and control the knowledge available to a society, and in particular the knowledge upon which its reproduction as a whole is based. While knowledge enables individuals to plan their actions and reflect on their outcomes, a society or institution cannot think, but merely anticipate the consequences of their actions within a specific knowledge economy. The limitations of historical knowledge economies may have played a crucial role in the collapse phenomena of past societies, as is suggested by the examples considered by the evolutionary biologist Jared Diamond. A history of knowledge of the Anthropocene could therefore also include a history of knowledge economies in which knowledge with ultimately planetary effects has been produced, shared, and reproduced, or failed to be produced or reproduced. Decisive for changes in knowledge and knowledge economies is the co-evolution of knowledge systems and knowledge communities. Understanding this co-evolution is basically the problem that Thomas Kuhn attempted to solve with his concept of paradigm shift. However, according to Kuhn, scientific communities are typically elitist and intrinsically conservative communities of experts, practicing normal science at a certain distance from society at large. In his neglect of the role of larger economic and political context, but also of practical knowledge, Kuhn was evidently influenced by the anti-communist spirit of the Cold War. This distinguishes him, for example, from Ludwig Fleck, and even more from the Marxist tradition of Boris Hessen and Henry Grossman, who emphasized the enabling role of the material culture of a society, as well as of broader knowledge traditions for science. To understand the epistemological dimension of the Anthropocene, the role of materiality is crucial, if only because the term calls into question the strict distinctions between the spheres of nature and culture. If, for example, the sediments to which the stratigraphy of the Anthropocene refers are no longer deposits of distinct natural processes, but hybrid residuals in which natural and human processes and their respective time dimensions are inextricably fused, then these natural cultural strata and the techno-fossils they contain become challenging objects not only for geology and historical science, but also for a scientific rationality to which the distinction between natural and cultural sciences is inscribed not only as a form of organization, but also a historical transformation of the Earth system sciences. But also as a historical transformation of the Earth system sciences, the Anthropocene can hardly be understood in terms of a Kuhnian sudden paradigm shift. Like all transformation processes of knowledge systems and knowledge economies, this concept and the pertinent epistemic community did not result from a single revolutionary turning point, but instead from a long-term, protracted development. The idea that the Earth has been fundamentally changed by human activities is anything but new. The popularization of the Anthropocene concept has even led to a now canonical list of precursors, including Georges-Louis Leclerc de Buffon in the 18th century, George Perkins Marsh in the 19th century, and Russian biochemist Vladimir Vernadsky in the first half of the 20th century. This list, however, does not adequately reflect the complex changes in knowledge production that underlie the concept and the formation of a community around it. Here, system theory and cybernetics, as well as the institutionalization of Earth system sciences, have played a crucial role, as has the International Geosphere-Biosphere Program, at whose meeting in Mexico City, Paul Crutzen put forward his objection to the Holocene, and more generally, the growing importance of international governance and environmental programs. If one wants to examine more closely such a long-term and complicated process in which not only many scientists and scientific organizations, but also NGOs and politicians have participated, one also needs suitable procedures to deal with historical big data, if one wants to understand this as a historical development. This requires methods of the computational humanities, in particular also methods that can be applied to tens of thousands of publications from diverse fields, but also a fundamentally new approach to understanding the co-evolution of knowledge communities and the knowledge itself. One such approach you have, those of you who have been present in Matteo Valaiani's talk yesterday have encountered, is the kind of network analysis that we pursue at the Institute with Matteo as a leading scientist, but also with Roberto Lalli, Manfred Laubichler, Dirk Wintergrün, and others. And so let me just resume with a few words how these two approaches fit together. The first challenge of such a network analysis is to conceptualize the interaction between social and semantic networks. And we conceive of them as being mediated by external representations of knowledge. To speak in Kuhnian terms, the emergence of a new paradigm can only be understood as a combination of societal and epistemic dynamics, but including the catalytic function of the external representations of knowledge, be it the instruments or the publications. So, as this is a key, we have sort of conceived different network structures whose interaction we want to study. So let me not go too much into detail here because that would be a bit of repetition from Matteo's talk yesterday, just to remind you that we think it's very important to look at the social networks, to look at the semantic networks, and to look at the networks that are constituted by the material objects of science, whether they be natural or human-made, and to look at the interaction between these different network structures. So Matteo has shown you how this works for the medieval Sphera community, which has been shaped by this network dynamics into an Europe-wide epistemic community that I think provided the background for the fact that some of the astronomical revolutions of the early modern period didn't remain revolutions of expert knowledge in astronomy, but actually captured a wide European attention across many fields because there was this networked shared knowledge in the background. A similar analysis, so this is again the spread. This is an older graphic from Matteo showing the spread of new knowledge coming from the Atlantic coasts, the new navigation experiences from Portugal, and then being distributed within the European network. So, but let me not spend too much time. Another thing that I also will just, very quickly allude to is the formation of the relativity community in the second half of the 20th century. The relativity revolution wasn't an event, a single event, paradigm shift with Einstein 1915 and done. It took almost a century, and it took an entire community to transform the knowledge. And that has been analyzed in detail, particularly by Roberto Lalli and colleagues. So back to the Anthropocene. It seems promising to extend such approaches also to an understanding of the Anthropocene and its intellectual career as a novel unifying concept integrating Earth system science and the study of human societies. But from the perspective of a theory of knowledge evolution, even more profound questions come into view regarding the very emergence of the new geological epoch as a result of the long-term history of human societies. To begin with, one may ask how the various proposals for the beginning of the Anthropocene are related to each other from such a perspective. They have, in any case, built on each other in a way that needs to be explained in more detail by future research. For example, without the so-called Neolithic revolution, the urban revolution wouldn't have been possible. Without the urban revolution, there would probably be no science because of the lack of a division between intellectual and manual labor, which was characteristic of the urban revolution. And without this division of labor, no scientific revolution would have been possible. And possibly there would also be no scientific revolution, no industrial revolution without the scientific revolution. Of course, this chain of events is not inevitable, but it may be a sequence of necessary prerequisites, but this remains to be examined in greater detail. It seems in any case remarkable that some of these developments can be understood as the emergence and accumulation of self-reinforcing feedback mechanisms within an increasing complex and increasingly connected world system. Consider, for example, the question of the relation between the scientific and industrial revolutions, central to the work of the economic historian Joel Mokyr. Whatever the precise causal relation between these two transformations may be, it is undisputed that during the so-called Second Industrial Revolution, at the latest, science and technological development were closely intertwined with industrial production. Since then, technological development, scientific innovation, and economic growth have not only been mutually reinforcing, but also began to involve more and more areas of socioeconomic development in an accelerated growth, including population, and you see some of these graphs here, including population growth, the exploitation of global resources, as well as global mobility and interconnectedness. This mutual reinforcement and expansion eventually resulted in the so-called Great Acceleration of the 1950s. And it had its counterpart in correspondingly rapid changes of critical parameters of the Earth system, such as the increase in greenhouse gases and soil erosion. In other words, the Earth system is actually no longer an Earth system, but a coupled human-Earth system. Besides the atmosphere, lithosphere, and biosphere, a technosphere has evolved with its very own dynamics. The self-reinforcing global feedback of economic and scientific technological expansion during the first and the second industrial revolution is just one obvious example of such dynamic mechanisms. How other related feedback mechanisms have unfolded is a question that requires further research at the interface between the history of knowledge and other disciplines. Not only with economic and social history, but also with environmental history and the history of materials, for instance. Most likely there is not simply one universal mechanism at work here, but rather historically specific interactions that are deeply influenced by their materiality. A history of knowledge relevant to the Anthropocene therefore has to include material histories as well. In German, Armin Reller, the chemist, has called them Stoffgeschichten, material narratives. And in the following, I just want to briefly consider two such examples in greater detail. And one is coal in Great Britain. Under what ecological, social, and epistemic conditions could coal become a key material of the Industrial Revolution? It is obvious that specific local prerequisites were required to start the self-accelerating and ultimately global dynamics in the use of coal. But was there just one such starting point, or were there many? How many early attempts were aborted? Which global dynamics were involved for the ultimate triumph of coal? And which are the conditions for its global demise? A well-known example of the local beginning of such dynamics is the use of primitive steam engines for pumping groundwater from English coal mines in the 18th century. Because of abundant fuel supplies, inefficiency did not hinder the use of such machines, and the interaction of specific ecological and technological factors created an incubator for the gradual development of such machines. The initially very inefficient steam engine thus developed in a local environment in which efficiency played virtually no role. In the 18th century, the baseload of the British fuel economy only gradually shifted from heating to industrial production. Only towards the end of the century, when the steam engine, coking processes, and new smelting furnaces had prevailed, did the consumption of fuel for production surpass that of households in terms of volume. The protracted energy transition from wood to coal was essentially a consequence of social and technological innovations that have prevailed in the course of around 1 century under favorable local ecological conditions. And so that's a bit the gist or the spirit of my story. You have very long protracted processes that take very specific local, ecological, but also political and cultural circumstances to onset. And once you have that onset, they have the dynamics of expanding on a global scale. In order to come to my second example, I will perhaps cut this coal example a bit short. It would be very interesting, and has been analyzed by our colleague Helge Wendt here at the Institute, how global coal history matters if you want to understand the beginning of the Industrial Revolution. But let me then quickly turn to my next example, my final example, which is the example of catalysts, the role of catalysts, one of the cornerstones of the 20th century chemical industry, and at its core is the Haber-Bosch process of ammonia synthesis. The Haber-Bosch ammonia synthesis process was indeed crucial for both fertilizer and ammunition production. This dual-use character led to the First World War becoming itself a catalyst that significantly accelerated the development of a particular type of chemical industry. Ammonia synthesis interfered in one of the most basic metabolic systems, the central production of foodstuff. Until the beginning of the 20th century, agriculture and thus the nutrition of a noticeably growing world population depended on natural nitrogen fertilizers based on Chile's salpeter, that is, on geostrategically unfavorable and limited resources. With the ammonia synthesis, synthetic, chemically, industrially manufactured nitrogen fertilizers were introduced. It is because of these synthetic fertilizers that the world population today can be fed. Without mineral fertilizer, the Earth could only feed about 1.5 billion people. To put it bluntly, the rest are alive thanks to the insights of modern chemistry. An annual production of about 150 million tons of ammonia provides, however, not only desirable and positive growth. In Haber-Bosch plants throughout the world, there is just as much nitrogen from the air being fixed in ammonia as there is in all global bacteria put together. Over-fertilized soils can no longer absorb this flood of nitrates. The nitrogen cycle, which such chemists as Justus von Liebig and Fritz Haber dreamt of controlling and completing, has been reopened at a dramatic scale. Agriculture has been transformed from a facility for the accumulation of solar energy into a subsystem of fossil energy transformation. By using artificial fertilizers from ammonia, far more fossil energy is invested in food production than in the solar energy that is bound in them via photosynthesis. We thus recognize as characteristics of the Anthropocene an increasing dependence on human interventions in cycles of the Earth system, interventions that in turn depend on scientific technological knowledge. But we also recognize how far we are from mastering the systemic consequences of these interventions, even at the level of scientific understanding. The success of nitrate, am I still right? The success of nitrate chemistry had far-going consequences, initiating further self-accelerating developments such as the rise of the petrochemical industry, as pointed out by the historian of science Benjamin Steininger. The superorganism of industrial petrochemistry could only arise in the cross-fertilization of nitrate, coal, and petroleum chemistry, and in the transfer of high-pressure processes and catalyst technology from the chemistry of nitrogen to the chemistry of coal and then oil. According to Steininger, the materiality of the 20th century largely arose on the eve of the First World War, in particular due to the transfer of the potential of multi-step catalysis from nitrate to hydrocarbon chemistry. You know, oh yeah, that's what I wanted to show you. So, you know, there are other transitions, but I will, rush to a close now. Let me just sort of mention that these other transitions are hardly considered in connections among each other. Typically, also as historians, science historians, we focus on particular branches: history of coal, history of chemistry, and history of digitization, about which I will be briefly speaking. But it's really important to take the Anthropocene as an invitation to consider these processes in conjunction. For instance, digitization. Digitization is closely linked to other global transformation processes, but also these relations are hardly understood. The big acceleration that I was mentioning earlier is hardly conceivable without the rapid development of information and communication technologies after the war. It's also evident that in the face of such global changes as climate change and the necessary transformations of our energy system, we will need digital control options. But there are also evident reasons to be afraid of them, because how we gain control over systems that have so much control over us. So how can we overcome this dilemma? How can we evolve a technical civilization that without abandoning our humanistic values, our human values? With regard to our current understanding, we are perhaps of the human Earth, of these coupled human Earth systems, we are perhaps at a point at which we were some 30 years ago when Earth system sciences was just emerging. So we think that it's very important to develop new transdisciplinary perspectives, to develop synthetic views on these dynamics, and we have tentatively called this new outlook geoanthropology. It deals with all those processes of the coupled human Earth system that are driving into the Anthropocene. So, to close, what does the challenge of the Anthropocene mean for the history of science? It lies not only in new questions, topics, and methodological approaches, of which I have tried to give you here some examples. The history of science may also gain new opportunities to use its insights and reflective potential for the development of innovative forms of knowledge production. As an example, I just mentioned the need for a reorientation of the current knowledge economy away from increasingly specialized, fragmented knowledge production towards more reflection, greater attention to systemic aspects, transformative processes, and global responsibility, including an emphasis on local perspectives and historical context. The historian of science, Yehuda Elkanah, who unfortunately is no longer with us, has once captured such a change he was always strong in coining such mottos. He said, we have to go from local universalism to global contextualism. And I think he was absolutely right on that. At present, we are trying out such novel forms of cooperative knowledge production for instance, in the framework of what we have called the Anthropocene curriculum, a kind of global intellectual laboratory involving academics as well as civil society, artists, people who are engaged in local communities, and so on. By curating new forms of engagement at the interface of the natural sciences, the humanities, art, and design, the campus initiative, jointly initiated by the Haus der Kulturen der Welt in Berlin and the Max Planck Institute, attempts to productively combine many facets of the Anthropocene research have been made, and they have been used also as a stimulus for the history of science and the history of knowledge. So I just wanted to end, with this very hopeful picture, the Anthropocene campus, and of course with an announcement that, my book will cover in more detail many of these aspects will appear soon. So with this, I thank you very much for your patience.